Well, you've probably heard this 10 times already. Welcome to Rice University in Houston, Texas. These are the three musketeers of astronomy in the department. Chris Johns-Krull, Pat Hardigan, and myself, Reggie Dufour. And you can see that we have several graduate students, 1, 2, 3, 4 graduate students currently. 2 got their PhDs last year, and my last one was 2 years ago. So we have also an active undergraduate program, which in the past 2 years, all undergraduate researchers have won the Heaps Prize or shared the Heaps Prize. So next slide. The research we do is quite varied, and Chris Johns-Krull is embarking on a relatively new program with graduate students working on extrasolar planet searches. Sure, you've heard about all these extrasolar planets, and now there are like 200 of them, and it increases daily. And hit the next return, yeah. And generally, there are 2 ways to search for exoplanets. One way is by transients across the disk of the star, causes the light to go dim. And the other technique is using radial velocity variations from the Doppler shift of not the planet. You can't see the planet, but it has a perturbation on the star. And so the star has a very small Doppler shift around the barycenter between it and 1 or more planets. The problem, though, is when you look at something like this, you say, wow, well, that's quite a big planet around the star, but it's actually a radial velocity signature of star spots. And so you have to be really careful how you do this. And there have been a number of false detections based on star spots. And the way Chris works around that is by observing the radial velocities at 2 very different wavelengths, in the optical and the infrared. And in the infrared, the effects of star spots are quite a bit less. His original research where he got his PhD at Berkeley was on magnetic fields of stars, and especially low-mass stars and young stars called T-Tauri stars. And these stars are just forming, and they have a accretion disk around them, and generally they have a very turbulent convective atmosphere and strong magnetic fields. And in order to measure the magnetic field of these stars, it's a tough observational problem. You need a big telescope and a giant spectrograph and a great high wavelength resolution. And what we have here is the little pinkish line is the spectrum of this star TW Hydra, and the yellow line here are basically fits if the star did not have a magnetic field. But because of the Zeeman effect, the lines are split, and the red here is basically a model fit to the data with a magnetic field of 2.6 Gauss. And you have to be very careful when you do this kind of work, and you have to have control. Objects like this is molecular CO, which shows narrow lines because the Zeeman effect doesn't affect them. And then the magnetic field across the star varies, and he can actually do a histogram of how the magnetic field varies across the area of the star. Next slide. Pat Hardigan works on jets from young stars, Herbig-Haro objects we call them. And basically, like the previous picture, you're looking now edge-on a protostar, and these protostars have jets. One of the interesting phenomena in astrophysics is you have jets from some of the youngest and smallest objects forming, and some of the largest and most massive and brightest in the whole universe, which is what Dr. Barrett was talking about, active galactic nuclei. So it's almost a ubiquitous astrophysical phenomenon of having accretion disks and jets. And Dr. Hardigan has made the most detailed studies of jets that have been done to date. And these are using the Space Telescope over a 5-year period where he imaged this jet in different wavelengths, and you can see the motion here that he detected, and he also mapped how the jet has changed in electron density, electron temperature, and hydrogen ionization.